Alright, in this example I'm going to look at the deflection of an electron through parallel plates. So what we're going to have is an electron that's accelerated from a negative plate through a hole in the positive plate. So we're going to have a plate here and then another plate here, but it's just going to have a tiny hole in it. We're going to have an electron here, and he's going to be going from the negative plate to the positive plate. So if it says the voltage across the plates is 240 volts. So if this is 0, this will be 240 volts. And the same electron then immediately passes between two parallel plates that are separated by 10 centimeters. So it says it's passing through them, so they must be like this. Okay, so he's going to come here. And the second set of plates have a volt of 100, and the positive plate are directly above the negative plate. So this is 0, and this is 100 volts. Determine the velocity of the particle as it leaves the second set of plates. So what's going to happen is he's going to be attracted to the positive plate as he moves through. He's going to sort of curl up, and then what we want to know is the velocity right here. The plates are separated by 10 centimeters, so this is 10 centimeters. And it says that they're 10 centimeters long, so this is 10 centimeters. So we got this electron. He's going to get accelerated up to some speed here. Then he's going to shoot out the edge of there, and he's going to curve as he comes up, and as he's coming up, he is going to change his trajectory, and we're going to figure out what angle and what velocity he's leaving at that second set of plates. So first of all, we'll sort of call this step 1. In step 1, we're going to find the velocity as this electron leaves these plates. To do that, I'm going to use an energy approach. I'm going to say that the potential energy of the electron is equal to the kinetic energy that it has as it leaves the plate. So it's going to convert this electrical potential into kinetic energy. The electrical potential can be given by the voltage times the charge, and the kinetic energy is 1/2 mass times the velocity squared. I'll solve this for velocity, so I multiply both sides by 2. And then I will divide both sides by mass. And then I'll square root both sides. So, 2 times my voltage, 240, times my charge on an electron, 1.6 exponent negative 19, divided by the mass of an electron, 9.1 exponent negative 31. So again, just to fill in those values, 2 times my voltage of 240 volts, times my charge on an electron, 1.6 times 10 to the negative 19 coulombs, divided by the mass of an electron, 9.1 times 10 to the negative 31 kilograms, will get me a velocity, and that velocity works out to be 9.2 times 10 to the 6. I've rounded here, and obviously I'm ignoring, I don't think I'm actually fast enough to really worry about it, but I'm ignoring any sort of relativistic effects that might occur. So that's how fast that electron is going to leave those parallel plates. So then the question becomes, how can we figure out how it's going to go out here in step 2 of this problem? Step 2 of this problem is a lot like a projectile problem. We have motion in the horizontal and the vertical direction. In the horizontal direction, we're assuming we have no acceleration. We have an initial velocity of 9.2 times 10 to the 6 meters per second, and we have a distance for this electron to go through of 0.1 meters. Since we have no acceleration, the thing that always connects the two dimensions in a projectile problem is the time, and since we have no acceleration, we can use the simplified uniform motion equation that the velocity is equal to the distance over the time, or the speed is equal to the distance over the time. So 9.2 times 10 to the 6 meters per second is equal to 0.1 meters divided by the time, multiplying both sides by time. .2 times 10 to the 6 meters per second. And then dividing both sides by 9.2 times 10 to the 6 meters per second. I'm going to find out it's about 1.1 times 10 to the negative 8 seconds. That effectively what I've done here is I've said if I shoot that electron out of those parallel plates with that speed, how long is it going to be in between the next set of plates? And I found that value to be 1.1 times 10 to the 8 meters per second. So I have the speed, I have the distance that it has to travel through as it goes through that next set of plates. So assuming there's no acceleration, I can figure out how long it's going to be in between those two plates. Now with that in mind, if I can find the acceleration in between those two plates, I can figure out how much vertical velocity this electron will take on as it's going through the second set of plates. So the next thing I have to do is I have to find the acceleration in that region. To find the acceleration in that region, the easiest thing to do is to use a forces approach. We remember that in between a set of parallel plates, the electrical force or the electrical field should be constant. So using that, we can come up with this equation that the electric field is equal to the voltage divided by the distance between the plates. In this case, I have a voltage of 100 volts, and I have a separation of the plates of 0.1 meters or 10 centimeters. And so I can say I have an electric field of 1,000 newtons per coulomb. Using that, I can get my electric force, which is going to be equal to 1,000 newtons per coulomb times the charge on one electron and that, don't need a calculator for that, it should just be .6 times 10 to the negative 16. See, I just move it up 3 decimal places because I'm multiplying by 1,000. So that's the force acting on that electron as it's traveling between those two plates. Now if I have the force and I have the mass, I can use Newton's second law to come up with the acceleration. F equals ma, 0.6 times 10 to the negative 19. Again, the mass of an electron is 9.1 times 10 to the negative 31. I just looked that up on my constant sheet. Newton's acceleration. And so my acceleration would work out to be 1.76 times 10 to the 14 meters per second. Okay, it's very big, but we're only going to be between these plates for a very small amount of time. So let's see how much that changes our velocity in that small amount of time. I don't know what happened there. There we go. So here we have an acceleration of 1.76 times 10 to the 14 meters per second. We have a time of 1.1 times 10 to the negative 8 seconds. We have an initial velocity in the vertical direction of 0, and we're interested in our final velocity. We can use one of the 5 equations of motion here because that acceleration is constant. Multiplying both, so our acceleration is 1.76 times 10 to the 14 meters per second. We're interested in our final velocity. Our initial velocity is 0, and we're between those plates for 1.1 times 10 to the negative 8 seconds. So I get a final vertical velocity of 1.93 times 10 to the 6 meters per second. So now I've got a horizontal velocity and a vertical velocity, and I'm asked for the total velocity. So I'd still have that last step of recombining these two components. So I'm going over at 9.2 times 10 to the 6 meters per second, and up at 1.93 times 10 to the 6 meters per second. So first of all, for my angle, I'll use tan theta, which is equal to 1.93 times 10 to the 6 meters per second, my opposite over my adjacent, divided by 9.2 times 10 to the 6 meters per second. You know, inverse tan, I can get an angle of 11.8 degrees. And to get the magnitude of that velocity, no one keeps resizing on me. You can use the Pythagorean result. Times 10 to the 6 meters per second squared plus 1.93 times 10 to the 6 meters per second squared, all square rooted. (9.2 exponent 6 squared plus 1.93 exponent 6 squared, square root answer. So I get 9.4 times 10 to the 6 meters per second. So my final velocity is 9.4 times 10 to the 6 meters per second. X 11.8 degrees Y. So that will be the trajectory it leaves those plates with.